Okay, good afternoon, everybody. Good afternoon. I've got a sore throat, but what's your excuse? Good afternoon. Wake up. Good. Welcome to second lecture in 61C. One of the great ideas we had is redundancy. So we had an error in the last lecture, so we get to repeat in this lecture. Dive straight in. So this is all to review. Last time we talked about numbers and how computers represent everything as a number. And when they're representing signed integers, nearly every computer today uses 2's complement representation. So we showed you these examples. Remember, with 2's complement, the top bit is a sign bit that tells you whether the number is negative or not. And to get from a positive to a negative number, you just invert all the bits and add 1, and that gives you the negative version of the number. Computers often work in fixed-size chunks, fixed words, and they can only fit a finite set of numbers. And if you try and store a number that's bigger than fits in that register or word, it's going to overflow. Last time we said underflow. That was a mistake. What we should have said is overflow in both cases. Whether the number is too big positively or too big negatively, it's still overflow. So overflow is the term you use when the magnitude of the number is too large to represent. Underflow we'll get to later when we talk about floating point. Underflow is when the magnitude is too small to represent. It doesn't happen with integers because when you add, subtract, multiply integers, you get more integers, and they're never too small. They're always going to fit in the word, but they may overflow, right? So both these cases are actually overflow. Another question we had on the list was about what is this carry in, carry out business? What does that mean? Well, when you're doing long addition, you do it digit by digit, going from least significant to most significant. And so the carry in is the carry coming to you from the least significant bits. That's the carry into this column. And when you complete the addition in this column, you may have a carry out that goes to the next column. So the condition that you get overflow is when the carry into the most significant bit is different from the carry out of the most significant bit. Okay, so that's the overflow condition. All right, so just wanted to clear that up. There was some questions on Piazza about this. Okay, all right. So today we're going to dive in and start talking about the C programming language. And we're going to start off by explaining one of the big differences between C and the other languages you may have used earlier on, such as Python, which is that C is a compiled language. So what does that mean? Well, I want to go back in time. So this is a real picture of a real computer, not a fake. This is a real picture. This is ENIAC. And ENIAC was the first electronic general-purpose computer. It did everything electronically, which meant it was really, really fast compared to earlier computers, which had mechanical pieces in them. Okay? And it was so fast, it could do a multiply in 2.8 milliseconds. So it did 300-something multiplies a second. And that was blazingly fast. And those were not small multiplies. This machine actually used decimal. So it had 10 decimal digits multiplied by 10 decimal digits in 2.8 milliseconds. That was blindingly fast. So this thing was way faster than any previous computer because it was the first electronic computer. No moving parts, just electronic. The one problem with this computer was, as you can see from this picture, maybe, you can guess, programming it was a little difficult. To program it, you actually had to go around and, these were dials that recorded numbers, and these were patch cables that set up the program. So to reprogram this machine sometimes took 2 or 3 days. And then you would run it for a second, and you were done with that program. Then you'd spend another 2 or 3 days setting it up for the next program. So it was great they sped up the computation part, but they needed to think about, well, how do we reprogram this thing? Another big problem with this machine was it was actually input-output bound. It was used to print tables. The development was started in the Second World War. It was used to print artillery tables, how big a shell, how much charge to go how far. The printer was the slowest thing, so this thing could do multiplies that fast, but when it came to printing the results, the machine was just sitting there waiting for the printer to go and print out all the tables. So in some ways, very poorly designed machine. But two of the main architects on this machine were Eckert and Mauchly, And they learned from this machine. They built this thing. This was the early days. People were just figuring out computers. And they figured out, well, this reprogramming is really one of the big challenges with this computer. We cannot spend 2 or 3 days rewiring the machine. You're basically building a new circuit every time you change the program. That's just not practical. And so they came up with this idea of maybe we should represent the program as numbers and store them in the memory just like all the other data the computer operates on. So the idea of storing the instructions for the computer as numbers in the memory came about from here. And what happened was they were working in this group. They had regular meetings. They had a visitor coming in, drop by the meetings, and his name was von Neumann. And von Neumann actually wrote down a lot of these ideas in this draft tech report. And a clerk at UPenn mistakenly mailed this tech report to everybody around the world saying, they have this idea for a new kind of computer. And lo and behold, von Neumann's name was on it, but not Eckert or Moakley's. And so von Neumann got all the credit for coming up with this idea of a computer that stored the program as numbers in memory. And Eckert or Moakley were understandably a bit miffed, also because this meant they lost the ability to patent the idea, because it had been distributed worldwide in this tech report. So anyway, that's why machines like this are known as, or these stored program machines, are known as von Neumann machines, even though von Neumann wasn't really the instigator of the ideas. It was Eckert and Moakley and their group. Anyway, so this report was circulated around the world, and they ran a workshop in the US for people interested in building computers. And this fellow called Maurice Wilkes, now Sir Maurice Wilkes, fortunately he passed away a few years ago, he came from Cambridge, UK, to this workshop in the US and said, this is a great idea. I want to go back to Cambridge and build one of these computers. And so he went back to Cambridge, UK, and he actually built the first general-purpose stored program computer, the first computer where the program was held as numbers in the main memory. This meant that reprogram it just required that you read the program from a tape into memory. Very quick, right? Very accurate, no bugs, from just loading the program. So you could do this very reliably, and that's the basis of all modern computers. And that's what we mean by a von Neumann computer, where the program is stored in the memory. So the real advantage of this was this quick reprogramming. And this was actually a binary machine, 2's complement, and it had 35-bit words. And it could also do operations on 17-bit words as well. So powers of 2 were not that popular back then for various reasons. They became more popular later on. Anyway, this is the first stored program computer. But what does that really mean? I'm trying to give you some more insight here. So let's peek ahead in the class and tell you a little bit about what's inside a computer. Well, what you have is the processor, the thing that does the computations, does the actual arithmetic operations, takes branches, makes decisions. And inside there, the pieces we'll tell you about later, the data path, registers, ALUs and stuff, the brains of the computer. And the other big piece is the memory, where all the data you operate on is stored. And these days, this memory is made up of a large array of bytes, 8-bit quantities. So every 8-bit quantity in the memory has a unique address to locate that byte within the whole memory. And the processor reads bytes from the memory, does computations, writes bytes back to the memory, and that's how the computation proceeds. The other important thing that happens is you need to do I/O. If the computer just worked on its own memory, nobody would know what it was doing, right? You need to actually communicate with the outside world in some way. So you have input and output. Now, where does this program live? Well, the program is just numbers in memory. So it's just stored in the same memory as all the data, right? So that program is just strings of binary ones and zeros that the processor understands how to interpret as instructions, which we'll get to later, right? So the idea of a stored program computer is very simple. Programs are just numbers held in memory. And also you have the data in the same memory pool, and you can flexibly allocate pieces of memory to program, pieces of memory to data. Okay. So this is one of these great ideas we have in computer architecture, these different levels of representation and interpretation. So what I just told you about is how programs are held in memory as numbers, strings of ones and zeros. So these strings of ones and zeros, they're actually pretty hard to code at this level. In the old days, people actually used to do this. They'd memorize the bit patterns and load them in one at a time into the memory space. Kind of tedious. A little while later, they figured out we can get the computer to help here. We'll come up with this idea of an assembly language, And all that assembler is a human-readable encoding of what the machine language words mean, right? So, like this bit pattern might mean load word. Load one word from memory into a register. And you write that out as LW, some register name, some addressing mode. So it's a human-readable text string, and then a program can take that text string and just convert it into the equivalent binary pattern, so you don't have to do that manually, right? So that's one step of interpretation, of abstraction. I'll just hide the bit pattern behind this text encoding of each instruction. But this is still tediously low level. As you'll see later, writing programs at the assembly language level is incredibly tedious, laborious, and very error-prone, right? So you don't really want to do that for any large program. And so these days, everybody writes in a high-level language. And in this class, we're going to go through C, because C is probably the lowest of the high-level languages, right? So it's barely over that border of being a high-level language. And people often call this the universal assembler because it's almost as low-level as assembly code, but it's actually portable to any given machine. Remember that different processors have different encodings here. There's no one universal instruction set. Every computer has a different encoding for what an add is, what a load is. And these days, the two big camps are the x86 family of machines from Intel, and then there's the ARM processors from the UK company ARM, which are used in iPhones and iPads and nearly every mobile phone on the planet. Those are two completely different instruction sets. But you can write the same C program, and the C compiler will figure out how to map that C code to one or the other of those instruction sets or any of the other number of instruction sets you might encounter, right? So it's low level, but it's not tied to a given machine. That's the goal of the C language, okay? So these are the different levels of representation. So this is the book, the C language book. This is kind of a really good tutorial. I remember reading a very early version of this book. That's how I learned C. Just go through the book. I know you've been given a load of chapters to read. It's actually a very pleasant read. It's a pretty well-done tutorial. So in this class, 61B is the prerequisite. You've done some programming before, including probably seen some Java. We use Python in 2 of the labs and in the project, and we use C for pretty much everything else in the class. Okay, quick poll. I'm just curious about your various language experience. So I'm going to go through a list of options. The first time you can answer yes, I want you to raise your hand, and then you can drop it after the next question, okay? So the first time you can answer yes, raise your hand. It's just a quick flash poll. Have you programmed in C, C++, C#, or Objective-C? Okay, that looks to be about 10, 15%, something like that, pretty good. I've programmed in Java. Okay, a lot of you took 61B. How many of you, 61B was your first time programming in Java? Okay, all right, great. I programmed in Fortran, COBOL, Argo 68, Ada, Pascal, Basic. Yeah, so. No, I've done some C as well. Okay, a few of you. All right. So, finally, none of the above. How many of you have never written a program? Okay, well, that's good. No, you're just too embarrassed to admit it. That's okay. It was actually a prerequisite. You've done some programming for this class. Okay, so some things to learn about C. So C is a very old language. It's been around a very long time, and I think 40 years now. And this is a quote from the inventors of the language. C is not a very high-level language, right? It's not a very big one either. It's actually pretty easy to learn. But its absence of restrictions and its generality make it more convenient and effective for many tasks than supposedly more powerful languages. And one of the great early credits to C was that it was used to write the first portable operating systems. So that was one of its initial goals. Prior to this, everybody had written their operating system in assembly code, right? Now imagine like these days, operating system distributions may be like 30 million lines of C code. Right? Imagine writing all that in assembly code and trying to make it correct, right? So one of the big innovations that C enabled was a portable operating system. Imagine that. You could run the same operating system code on different processors. That was a new thing. And so C has retained that ability. It's the number one choice for any kind of low-level systems programming where you need very direct access to the hardware, right? But what's actually surprising is, although that was its original motivation, writing low-level operating system and low-level code, it's actually become very popular for applications programming too over the years. And I pulled some data I found very interesting off this website. So TIOBE is a firm that does language popularity. This does, language beauty contests. How popular is this language or the other language? And what they do is they survey lots of different websites to see, how common are people searching for, how much code is there for different programming languages. And it gives you a reasonable idea of the popularity of different programming languages. How much are they used? Okay. Number one language is C. Pretty surprising maybe to some of you. It's the most popular programming language. Java's number 2. But what's also interesting, the next 3 are all C variants: Objective-C, C++, C#. And Java itself, the syntax was based on C because it's so popular. So C really is, this very important part of computing. It's very low level. It doesn't have a lot of the fancy new programming language concepts, but it's very low level based that lets people build applications. And so you'll be learning about it in this class. And just another chart is over time. These are years, so from 2002 to 2014. And, C is here. And it's kind of maintained its popularity over the years. Other languages come and go, but C is there pretty solidly over time. Now, we're not going to fully teach you how to program in C. You'll have to, one thing about programming languages, you cannot learn a programming language from lectures, right? It's like, teaching you how to ride a bike in a lecture, right? You just have to go and do it and use the language, and project 1, you'll be doing a significant amount of C programming. But places to get more resources, to get more help with that, as well as the staff, is these books. So the Kernighan and Ritchie book is a must-have. Coming from Java, you may want to look at this chapter, which tells you how Java differs from C. That might be useful to you to make the transition. And Brian Harvey has a set of notes that are helpful too. So we're going over the key concepts of C today in the next couple lectures. First, let's get back to this issue about compilation. So C takes a program, which is just a file on disk that has, your characters in there for your program. And then the compiler translates that into machine code. And that process is called compilation. So from your C program, high-level C program, generate that low-level machine code, strings of 1s and 0s. Now, unlike Java, the Java compiler generates something called bytecode, which is, there's only one kind of bytecode for Java, and any machine can run that bytecode by interpreting or translating it dynamically at runtime. But there's only one kind of bytecode in Java that runs on any kind of machine. Now, C compilers are different than that because they generate machine code for the specific architecture you're targeting. For example, an x86 machine versus an ARM machine, those would generate 2 very different binaries from the same C program, right? And there's also C compilation is a multi-step process. I'll talk about a very simple view of that today, and we'll go in that more detail later. So every individual piece of your program, you can put in a separate file. The standard extension is .c. And those .c files are each compiled to individual .o files, where O stands for object code, which is machine code. Then you take all the object code files that make up your entire program, there may be many of these, and you link them all together, including standard libraries, to build a final executable file that is just a very big program with all the machine instructions in for your whole program. And that's called the executable, and that can be directly run on your computer system. So here's a sort of picture of that process. So at the top, you have the text files representing your C source code. And I have 2 files here, foo.c and bar.c. They all get compiled separately into 2 object code files, foo.o and bar.o. Then you take those object files that are specific to your program, then you'll link them to library, pre-built object file libraries, lib.o, some kind of library, That is, libraries that are, application independent, things that you use everywhere. For example, a sine function or a cosine function might be in a library code. So you don't have to write that every time you use it. Then these are all linked together by a linker. Just pulls all those pieces together, figures out where they're going to sit in memory, packs them all into one chunk, and builds this final executable. So this is all done for a specific machine, an operating system in mind. So the resulting executable will only work on one machine and one kind of operating system. You cannot move it across different machines. You have to recompile if you're going to a different machine. So the advantages of doing it this way is very fast. This is basically the fastest language you can have, really. It goes straight down to the machine code because it's optimizing for that particular architecture from the get-go. It knows exactly what it's targeting. It's a very low-level language. It's very easy to write, very high-performance code. The other thing about splitting your program into separate files, you only have to recompile the pieces you change. Typically when you're developing and debugging, you'll find a bug, you'll fix it. It'll just be in one file, you have to fix it. Only that one file has to be recompiled. But you still have to link everything together. So why do people use C? Well, it's because this low-level access. You can get deep into the heart of the machine and access all the features, and that's part of the reason we're using it in this class, because we're going right down to the hardware level. Now, some of the problems with compilation. Well, one thing is those files you generate, those programs, they only run on one machine. They're useless on another platform, unlike Java bytecode. So if you change from MIPS to RISC-V, for example, you have to recompile all your code. And if you change from, say, Windows to Linux on the same machine, you have to also recompile your code. So this is called, porting your code to a new architecture. And this is something that one of the things you'll see with C code, it has a lot of ambiguity in how things are done. And so your program may work on one machine, but because you relied on some effectively undefined behavior, when you move to a different platform and recompile, it may not actually work. So there's some thought needed to actually make C code that is truly portable between different architectures. Another issue is this process can be a bit slow if you're used to interpreters. So every time you change your code, you have to wait to recompile it, to link it, and then you can run it. And that can slow down your compile, edit, debug loop. But like I said, some things that help here that make only rebuilds the change pieces. But you're limited by this sequential piece of linking everything together to make a final executable before you can run it. And this is like another tiny example of Amdahl's law, right? No matter how much you parallelize all the .c to .o files, at the end there's a sequential link script that pulls everything together. And so I know that some companies that build very large programs, CAD companies, people building operating systems, they do these builds overnight because it takes, and most of the time is spent in this final link step of pulling all the pieces together and building that final executable. It can take hours in some cases for very, very large programs. One other difference with C is than most languages you'll have seen is not all the work of translation is done by the compiler itself. And the very important part of the C world is this C preprocessor. So this is standard, and every C compiler uses this. And what this does is take a first pass at the text you type in and macro expands it into an expanded version that's what the compiler actually sees. So, you have your foo.c program here. There's a C preprocessor. Now, this is hidden to you. You just type, the compiler command. But internal to that, there are these two phases, preprocessing and then actual compilation. And this generates an intermediate file, which then goes to the compiler. Now, some of the things this preprocessor does, it replaces comments with white space. So the preprocessor is a thing that removes all the comments from your code, so the compiler never sees them. All right? Another thing it does, it lets you include files. So you can have one file, you do a hash include of some file name. What the preprocessor does then is fetches that file, inserts it in line into that intermediate file before the compiler sees it. So the compiler never sees all these other files that you include. It just sees this one stream of text characters coming in. All right, so the hash include is handled by the preprocessor, and it pulls in a file. So, one thing I forgot to say, all the C preprocessor commands are preceded with this hash symbol, or some people call it a pound symbol. I grew up in the UK, and that's not a pound, right? That's a hash, right? It's a hash symbol. everything that the C preprocessor does is preceded by that. So if you just use regular double quotes, it just pulls that file from the path you gave relative to the directory you run this in. You'll then take that file and just insert it in line before it gets to the compiler. If you use these angle brackets, that tells the preprocessor to go look in a special standard place for the header file. And this is how you find the header files for standard libraries on the machine. One of the important ones is standard io.h, which is a standard way of inputting data and outputting data from your program. Right? So that has angle brackets, which tells the preprocessor, go look for this header file over here. These are called header files, the .h's. Another thing you could do to the preprocessor is define macros to save you typing the same thing over and over again. Right? One example might be you want to use the constant for pi. Right? You don't have to type 3.14159, whatever, every point you use pi in your program. So what you can do is define a symbol, and this is done in the math library, m_pi, to be equal to the string representing the number pi. Right? So now anytime you want to use pi, you just say m_pi in your code, and the macro processor in the C preprocessor will then, every time it sees m_pi, before it gets to the compiler, it replaces it with that number string. Okay? So the preprocessor lets you define some symbol to be expanded to some other set of text. Right? So that's one way. It's commonly used for constants in this way. Another powerful thing the preprocessor can do is conditional inclusion of code. So you can actually, in the preprocessor, say, if this condition is true, for example, I'm compiling for a RISC-V machine, use this piece of code. Else, if I'm compiling for a MIPS machine, use this piece of code. And then you can have conditional compilation. Only the piece that is relevant will be included and passed to the compiler. So the compiler won't even see the code. That doesn't matter for the platform it's running on. Or there can be other things like compiling it, with graphical interface or without, or other kind of compile time options. So you can have conditional inclusion as well. If you want to dive more deeply into what the C preprocessor does, there's a link here that gives you the full documentation for the preprocessor. It's kind of its own little world. You can dive down in there. If you want to see what happens in your C programs, there's a -save temps option to the GCC compiler, and it'll produce the .i file that'll tell you what happened in this midpoint. By default, this is just not produced, and it streams straight from the preprocessor into the compiler. But if you want to take a look, sometimes it's useful debugging. You can look at this here. Okay, but most of the time, most of you won't have to worry about this. You'll just get to understand these as parts of the C language, these preprocessor commands. Okay, so we talked a little about C. Now let's try and do a comparison with Java and Python, give you some reference point so you can see the differences between C and languages you may already know. So most of you have done the Java. So C is a function-oriented language. It's based around functions. So it's not really an object-oriented language in any way. C++, the follow-on, is kind of the object-oriented version of C, but C itself is just based around functions. Whereas Java, as you know, is object-oriented. So the unit of programming in C is a function. You sort of work a function at a time to build up your program, whereas in Java, you'd be working in classes and abstract data types. So when you compile a C program, like I said, you get architecture-dependent code, a binary that only works on one kind of processor. Whereas with Java, you get a bytecode that should theoretically run on any kind of processor that has a Java bytecode interpreter on it. So when you actually run a C program, it's directly run by the hardware. The instructions in that program map one-to-one to hardware instructions, and the machine runs them directly. In Java, when you run a Java program, those bytecodes have to be expanded into those individual machine instructions, right? So here's an example of what the code looks like. This is, printing hello in C. So notice this is a preprocessor command to include stdio.h. And what's in this file are all the standard definitions the compiler needs to understand that printf is a standard library function that has a certain type. That's why you include this here. And it's just printf, which is print formatted. Hello, /n means put a new line at the end. Right, so this quoted string will be produced as hello. And then you say return 0 to say the program will exit with a 0 condition, which means it executed correctly. Right. And here's the equivalent in Java that most of you will have seen already. One of the big differences between C and Java that affects people as programmers probably the most heavily is Java has automatic memory management and garbage collection. So it takes out the trash for you, right? So you forget some object, you stop having pointers to it, the Java system will clear that away for you. In C, you get to do all that yourself. You get to allocate memory and free memory, and if you don't free memory, you'll get what's called a memory leak, which means your memory fills up with stuff that that shouldn't be there, that's not being used. And if you do free it and then use it, you just get bugs. So it's very error-prone if you use the garbage collection. At the same time, it's a double-edged sword, very error-prone, but very powerful. It can be very fast, and you can customize the memory allocation to the task at hand, right? But all the memory allocation, allocating chunks of bytes to hold things is all in the programmer's hands in C. We'll talk about in a few days time, next lecture or two. But you have to manually allocate regions of memory and manually free them. You can't just create new objects anyway. You have to allocate and free the space for them. So comments look very similar. A lot of the syntax of Java was borrowed from C, so Java will be accepted because there's so many C programmers out there. They needed to make Java look like C to make it acceptable. So comments like this. Now, Java has these dash end of line. Newer versions of C also have that. And what's an interesting historical tidbit is the predecessor of C was a language called B. The predecessor of B was a language called, it's called BCPL. Right. And this was developed in Cambridge, UK, by a guy called Martin Richards. And BCPL was one of the very early systems programming languages designed to work at this low level. BCPL had this comment syntax, and it kind of reemerged later. It kind of disappeared in B. B was a simplified version of BCPL, and C is an expanded version of B. But that's the history. So this comment syntax actually came from BCPL. So constants in C, you can either use the hash define I just mentioned, which remember is a preprocessor replacing the text. The preprocessor, before it gets to the compiler, takes that text string for the symbol and replaces it with the expansion that you gave. Right? Hash define pi to this number. That's one way of having constants in your code. Another way in the newer C standard, you can actually have a const declaration we'll talk about to define a variable as being constant. Java, you have the final keyword, equivalent thing. So C has this preprocessor, Java doesn't. C has this restriction that all the variables you use in a block of code have to be declared at the top. You can't just declare them as you need them along the way, at least not in the older C variants. That's sort of come in with the newer C variants, but traditional C, all the variables declared at the top of a block, which is kind of annoying, but that's the way it is. So old school naming conventions, you separate the components of a name with underscores, sum of squares with underscores. The new hip thing is, this camel case where you have capitalization to separate the components. I guess I'm not hip because I find this far easier to read than this. Just take a little bit more space, but you at least know when an acronym is an acronym and not just something here. So as I mentioned before, to get at a library, you include, now these .h files we'll talk about later, those are header files, and they're just other files that are pulled in and put in line. And remember, the compiler, when it's compiling the code, is only looking at one file at a time. So when you compile foo.c, that's all the compiler sees is foo.c, right? So you have to tell it everything about anything that's in foo.c so it can generate correct code. So the job of the header file is to tell the compiler about all the things that are used in that one file, what their types are and everything else, so the compiler can do the right thing, right? And in Java, you have the equivalent is importing a library, import IO, whatever. So C types. So you have, integer values, integer variables. So int variable 1 equals 2. You have float is single precision, floating point numbers. Double is double precision, floating point numbers. So this is more precision. This is less precision. You have both signed integers and unsigned integers in C. And almost all machines today, those are 2's complement integers. But unsigned means you want to treat that collection of bits as an unsigned number, right? If you want a bigger integer, it's called long, right? It gives you a bigger integer, right? But how big are these? Well, this is one of the curiosities of C. C was designed to make it easy to write efficient code relatively portably, but really efficient code for a given platform. And so they left some flexibility in the language spec to how big integers would be, right? So unlike Python, basically, you can make them as big as you want. The machine will just do the right thing. It'll create enough bits to hold your integers. In Java, it's 32 bits. That's define what it is. That's how big ints are. But in C, it depends on the computer. So an int can be 16 bits, 32 bits, 64 bits. In fact, it could be 35 bits. It could be 43 bits. Different machines over time. Some of the machines C was ported to were not Power 2 sizes, right? The important thing was the programmer could use whatever width was natural to the machine as an integer. And the idea of C int type is the int type should be the word size that's the most efficient for the processor platform you're working on. That's why it has this flexibility, right? But also why sometimes it's hard to make the code portable, because ints will be different sizes on different machines. The only guarantee you do get is that there's an ordering of, a monotonic ordering of the integer sizes. So the smallest, almost the smallest ones are called shorts, right? A short is guaranteed to be at least 16 bits, right? But it could be 17 bits. If you're programming EDSAC, it'd probably be 17 bits, right? Int is guaranteed to be at least the same size as a short and possibly bigger. So ints might only be 16 bits. A long, though, is guaranteed to be at least 32 bits, but it may be bigger. And finally, there is a long. It's a great name for a type, like a long, which is longer than a long and maybe, or maybe not. It can actually be the same size as a long. Depends on the implementation, right? All of them could be 64 bits. It's actually valid. Some of the crazy supercomputers, everything's 64 bits. You want a byte? No, you get 64 bits. Everything is a 64 bits on those machines, right? And that's valid C code. So when you're trying to write portable C code, you have to worry about this stuff. Constants. So I mentioned before, this is a different way, other than the preprocessor, of defining a constant. So this is like a variable declaration, except you have this extra word const that tells the compiler this value, this variable, has a value that doesn't change. The program's not allowed to change the value of that variable. It's always going to have this value, in this case, 1.618. So any of the standard types, you can just add this keyword const in front and make it a constant. Another feature of C is the idea of an enum. That's short for enumeration. And this is when you have a menu of choices that you want to represent as integers, but instead of manually allocating, this one is coded as 0, this one is coded as 1, this one is coded as 2, you can just write the symbols. For example, for cards, you can say, I want clubs, diamonds, hearts, spades. And the compiler will allocate numbers to those. But in the rest of your program, you just use those symbols to refer to that option amongst those different suits, right? Okay, so we're going to do a little clicker test. Now, do any of you have a clicker yet? Okay, right. So it's my first time using clickers. It's a clicker test for me too. We're not going to count today in terms of participation, but just as a debug cycle. We'll actually start serious clicker usage on Tuesday. Remember, we're only recording participation, not whether you get it correct or not. Okay. So, oops. So if you start it up, your clicker up, you should see CS61C on the clicker coming up. Yep, people are getting that. Okay, I think those still work. All right. So let me just do this one. Doesn't count for anything. Just use A is for you prefer Coke, B is you prefer Pepsi, C is you don't drink either. Right? Let me just start. I just want to see if, yep, I'm getting clicks coming in. Any more takers? Yep. I'll let it go for 1 minute. Seems to be about right. Can we get 200? Okay. All right. All right. So I guess Coke wins. There's a few out of band. Oh, I guess that's the beer column. Okay. Beer and wine. Yeah, okay.
Beer wins, right?
Beer wins, okay. Of course, none of you are of legal age, right? So you shouldn't be drinking that stuff at all. Okay. That was fun. Yeah. Okay, well, that was fun. Well, I guess it works. All right. Okay, let's do a real question now. Okay. Remember, this is just, I'll do this just as a test. It doesn't count for anything. We'll give you an idea how things will go in the class. All right, so this is, see if you understand this. What I'm going to do is ask everybody to answer this question by yourself first, and we'll take a clicker poll, and I'll put up the results. Then I want you to spend a minute or 3 minutes talking to each other, see if you're going to change your answer, then we'll do another poll again. All right? And for those who don't have clickers, I will, maybe I'll do a quick hand poll at the end for you guys, so you don't feel excluded from the fun. All right, so this question, I'll just explain the question. So there's 2 different ways I've mentioned about defining constants in C code. The first one is using the preprocessor, hash define pi is 3.14. Another way you can do it is by using the const declaration, const float pi equals 3.14. So which of the following 5 statements is true? The constants, so I'm using capital pi for the preprocessor version and lowercase pi for the const version. Uppercase pi and lowercase pi have the same type. You can assign to uppercase pi but not to lowercase pi. Option B. Option C, code runs at the same speed whether you use uppercase pi or lowercase pi. D, lowercase pi takes more memory than uppercase pi. And E, both behave the same in all situations. Okay, so let me start this up, and I'll just let people vote for a while. I'll give you a minute. The first part was supposed to be by yourself. Second part is you get to talk to other people. Some people like talking to themselves, apparently. Okay, we think we have pretty much everybody in there, almost. Let's stop it. Yeah. Okay. Let me, okay. So that, a lot of people liked D. But it's pretty even support for everything else. So, now at this point, I want you to look at these results, spend a little bit more time, and come back to you I'll give you 2 minutes. Then I'll do another quick poll, see if anybody changes their mind, all right? So this is the pyramid tree. This is what you're supposed to talk to everybody else, okay? So, and it's okay to completely educate your neighbors about what you think the right answer is. Okay, 2 minutes. Yeah. Okay, 2 minutes are up. I'm going to run it again for 1 minute. Okay, I'm going to stop it there. Not everybody voted that time. Before I put up the results, I want to give those of you without a clicker a chance to participate. Okay, so those of you without a clicker, it's just a rough show of how many thought A? One or two or three. How many thought B? One or two or three. How many thought C? A few more, maybe 10, 15. How many of you thought D? Yeah, you guys just seen the last poll. Okay, all right. Quite a few there. That was obviously the winner. How many thought E? Oh, a few more. Okay, so I think D was the most popular. C had a few more. Okay, but on the results here, yeah. Yeah, that's wrong. It's the wrong answer. Okay. This was a bit of a tough question, but I'll go through now. Hopefully this will help you understand, see a bit better. So let's go through these. So option A, constants pi and pi, uppercase pi, lowercase pi, of the same type. Well, what's the type of the hash defined? What type will the compiler think that has? Yep. So what happens when it hits hash defined pi 3.14? Then it sees pi in the code somehow. What does the preprocessor do? Just inserts the digits 3.14. So the compiler just sees 3.14. What type does that have? It's actually a double, it's C rules. But it does have a double type, actually. So what's the type of pi, the lowercase pi? It's a float. So actually, they do have different types. One will be a double, and one will be a float. In fact, the pi, it's not clear what type it'll have. Depends what's around it, actually. So it's even worse than it's different. You don't even know until you see the code around that 3.14 in the text. B. Well, we already said that the question says you cannot assign to lowercase pi. I already said that. That's the purpose of the const. That means it's constant. You can't change it. But, can you assign to uppercase pi? Think about what happens in the flow of the compiler. So pi is seen by the preprocessor. It converts the uppercase pi into the digit string 3.14. So saying you could assign to pi is saying I could say 3.14 equals something else. Right? And that wouldn't make sense. Let's define 2 equals 5. That'll really make debugging fun, right? so you cannot. Yep. That's a great question. So the question was, what happens if you define pi in 2 different parts of your code? So say I'd hash define pi 3.14, and somebody else said, I want pi to be 3.14, 159.265, whatever. What will actually happen is if both of those are seen by the preprocessor, it will complain and say, you've defined it twice. Now, this makes it difficult. If you're writing those files, they're going to be included in some other text. You don't know whether somebody's already defined pi or not. And so one of the things you use, one of the idioms in C is you have, remember I talked about the hash if conditional inclusion. There's an option which is hash if not defined pi, then define pi to be this. So you can check to see if somebody's already defined it. And if not, you'll add the definition. Otherwise, you'll use the pre-existing definition. So that's a good question, though. Great question. So you cannot assign to pi because when it expands out, it's going to be 3.14. So if you say 3.14 equals something, it doesn't make any sense. So you cannot assign to symbol pi either, uppercase pi. So going from the bottom, we've already described why they don't behave the same in all situations. For one thing, when pi is expanded out to the string 3.14, uppercase pi, it really depends what's around it, how that's interpreted, whether it's a double or other strange things can happen to innocent digits hanging out by themselves in a C program. So it doesn't behave the same as the symbol pi, the lowercase pi, which is a variable. The compiler knows that's a variable that has a constant value, right? So they're not going to behave the same in all situations. Already sort of given some examples of that. So now these 2 choices, C and D, those are the most popular choices. D was the majority decision. Well, it turns out neither of them take any memory space when you have a good compiler. They're just constants, right? They just get elaborated away, and they just get folded into wherever computation's going on, right? So they both work the same way. If you need to store 3.14 in memory to hold that number, you do it in both cases. The compiler treats them just the same. So they don't take any more memory space. So the correct answer is C. If you use them correctly, it doesn't matter which one you use. The compiler's going to do the same thing and just treat them as constants and generate the same code. So they run at the same speed, whether you do hash define pi or const float pi. Excuse me. So the decision whether to use one or the other really depends on hash define was the old style way. And one of the reasons we had C preprocessors was it was difficult to fit all of the compiler in memory when people first started using C compilers. So they broke up the compiler into pieces. And this was one of the pieces that would run separately, reading the program in, doing the pre-processing, writing it out to disk. Then the second phase would read that from disk. The compiler would do all the other work and write it out. So that was one reason it was done that way. Const is a relatively new addition to C. It's a better way usually if all you want to do is define a constant. Okay. All right. So that was our first clicker test. It doesn't really count for anything. So this will be the format we'll use for the future clicker questions. So the idea is initially you should answer by yourself. Then we'll look at the results. Then you get to chat to everybody, peer instruction, and then you get to change your mind. Then I'll go back over but we'll both go over the actual results then. Okay, so quick administrivia. So homework 0 is out. So there's 2 pieces to this. The mini bio is due in your lab section. So labs start tomorrow, in 3:30 SOTA. And so remember, our cycle starts at the Tuesday lecture. And after Tuesday lecture, you'll have the corresponding labs on Friday, Monday, and Tuesday. Right? That'll be all those that have the same content. And so in your relative lab section, your mini bio is due. The rest is due Sunday, February 1st at 1 second before midnight. And after that, you start using up your slip days. So 3:30 SOTA, we're expected to be open. They have been renovating in there. They should be open on Friday, we expect. If not, we'll be sending out announcements, so watch out for any announcements about what to do if it's not open. There is also an office hour schedule for the TAs up on the website. And remember to bring your clickers for class next time. Okay, let's dive into the rest of the lecture. So now what I want to do is give you sort of a quick start introduction to what do C programs look like, how do you write them. First thing is, C is based around, were there any questions before I run ahead? Nope, okay. So C is based around functions, and so every function has a type of value it returns. So, this is int function number of people, and this one has no arguments, just returns the value 3. So the return type of that function is an int. You can have a float or a character. The character is one character in a string, a char. And you have to declare the type you return from a function. And it can be any type and it's placed there. If you don't need to return anything from a function, if it just does some operation on state in the machine, updates memory, doesn't return a value, you can just use void instead. Void means nothing. So this function doesn't return anything, okay? That's the void type. Also, all of the arguments that are passed into the function also need their types as well, okay? And you have to declare this before you use them. So you have to order your program, your .c files have to have all the declarations of your functions before you use any of those functions. In C, you can write structures, which are groups of related variables. For example, you can define a song to contain an integer with the length in seconds, another integer encoding the year it was recorded. Then you can just declare a struct just by using this name. So this typedef keyword here tells the C compiler, I'm declaring a new type. It's a struct. It looks like this, and this is the name I'm giving the type. So I'm creating a new type, which is a struct. That's what the typedef does. Then I can just have declarations of here's a song, name song1, and I can set the fields using this dot notation. So song1 dot whatever is this, etc., and I can create a second song like this, right? So that's how you get to members of the structure. What are called members? Yep. Yeah, so the question was, is it case sensitive? Does upper lowercase matter? The answer is yes. So it is case sensitive. Sorry, there's a question over here. Oh yeah, this is a bug. Thank you. This is a bug in the slides, yes. These should be lowercase. That one should be lowercase, and that one should be lowercase. I think that is a PowerPoint-induced capitalization bug. Sorry about that. Yes. Just take a note and fix that. We'll fix that in the slides we post on the web. So simple C program. So C programs start at main. It's like the entry point. Where does your program start running? It starts running at the function called main. So older style C, you didn't have to type as much, but that meant it was more likely you'll get errors. So newer style C, you have to declare a lot more. So you have to, for hello world, you include the standard I/O library, the header file for that library. So what's in that .h file are the types of all the functions in the standard I/O library. So the compiler knows what the argument types should be when it calls a particular function, and what return types will come back from that function. And so it can generate the correct code inside this individual .c file. And so here, main, we just say void. It doesn't take any arguments. We're going to return the exit code from the program. In this case, we're just going to return 0. And this is print formatted, which just prints a string. The /\n is the way of encoding a new line in that string. So the backslash is like an escape character. So \n means new line. So this will print a new line, hello world, then another new line, and then exit and end. So that's hello world in C, pretty simple. Now, what actually happens when a C program starts up? Remember, you're going to compile all the .c files into .o files, link them all together to make an executable, which is just a big lump of bits that's going to get loaded into the computer memory when you start running it. So when a program starts, that executable file, the operating system takes it, puts it in memory, just copies all those bits into memory, then it sets up a stack, which we'll talk about later, and then jumps into the defined piece of code that's linked in with your code always, the runtime library. It kind of runs, so it jumps into the program at that point, but it's not entered main yet. It runs into some code that sets everything up, and then finally it will jump into your main code and start running your program, right? Later on, we'll talk about how to get command line arguments into your program, right? So, you type, my program on the command line and hit return. You can hit my program and some options and hit return. We'll tell you how to do that a bit later on. You need to see a bit more C to understand how that works. Okay, but that's how a program starts running. So here's a bigger sample program. So this one, we're going to use two kind of libraries. We're going to use the standard I/O and also there's a standard math library, math.h. So we're going to print a table of signs. So you see we're going to declare a variable. Notice all the variables are declared here. Int angle degree, double angle radian, comma pi, comma value. So notice you can declare several things with the same type by using commas in between over here. Then print a header. So these are comments between the \*. So we get pi by calling a math function. We could have used the constant m_pi, but here we're going to call a function arctan. So the arctan function, the fact that it takes a double value and returns a double value is encoded in this header file, right? And notice the header files have these angle brackets. The include is angle bracket with the file name. That means go look for it in wherever the standard library files live, right? Not in this directory, but somewhere else, the standard place, right? So these are standard files. That's why they have the angle brackets. And you just print the value of pi. Then you print the header for the table. And now here's a little loop. Initialize the degree to 0. Step this through to 360 while it's less than or equal to 360. Calculate the angle in radians. Calculate the value. Print it out. Now, print formatted. Printf is printf. The F stands for formatted. And that string you include can include special symbols that indicate how to format variables that appear in the output. So this string includes a %3d. That means print an integer in decimal using 3 digits. All right, so that's how it's formatted. And then %f means print a floating point number however you want to in this general F format. So now there's a comma here, and then these two arguments, angle, degree, and value. So this is the integer that will be formatted and printed here, and this is the floating point value that will be formatted and printed here at that point in the string. Then you increment the angle degree, and this will loop around until this condition is false. Then it'll just drop through, and we'll be done. And this program is missing a return. It should have a return here, return 0 to exit correctly. Okay, so that's a very simple program. When you run this is the output you get. Notice that these have been aligned. It's formatted to 3 digits. That's why these line up. And this is the floating point formatting. I think by default it's 6 decimal digits are used in the formatted. So you get this formatted output using that printf command. Okay. Any questions? Yep. Can comments in C expand through multiple lines? Yes, the ones that have the slash star will continue to the next // and they can span multiple lines. Yep. So in newer Cs, you also have the \/, which just goes to the end of the line. So both formats in C. So declaring variables in Java, declaring variables in C, it's similar to Java with a few differences. One thing I mentioned before, you have to put all the variables at the top of each block of code. You cannot just do them as you use them. Although newer C standards, I'll talk about those later, I'll let you do that. So it'd be incorrect, for example, to say for int I equals 0. You cannot declare I inside the iterator here. You have to do it ahead of time. Okay? The reason for this is earlier compilers couldn't handle this, and you had to tell it what was coming up early so it could handle it. So control flow, basically you can see, if you're familiar with Java, it's very similar because Java basically copied all the C control flow constructs. So, if then else, if else, while, do, while, for, which has 3 components. You initialize the variables here, you check the exit condition here, and then you update for each iteration in the last component here. There's a switch statement which takes an expression, and then based on the value of this expression, you can have cases that say, if this expression has this value, execute these statements, or if it has these value, execute these statements. One tricky thing with the switch statement is that control flow will come down into here, then jump into the matching case, but it'll keep going unless you put a break in, which tells it to stop and jump to the end of the switch statement, right? So you could have something that matched here would by default just run through all the other code unless you put a break in between each of those cases, right? So that's a very common bug. People forget the break statement in between those cases. Another important thing is what evaluates the true or false. A lot of those loops, control constructs had to control some kind of Boolean, true or false, whether to continue or not. So what evaluates the true or false? Well, C takes this model of integer 0 is false. It's equivalent to false. There's a special symbol null, which corresponds to a null pointer. We'll talk about pointers at the end of today. That also evaluates the false. Basic C doesn't have an explicit Boolean type, right? It just relies on ints being 0 or not 0 for a lot of these checks. So true is anything that isn't false, right? So 0 is false, null is false. Everything else is true. It's kind of like Python in that way. I won't go through all these, but these are the various operators. They're very similar to Java. Has a lot of the same. Just Java you borrowed this from C. So notice it has these augmented assignments. You can say, x plus equals 1. And that'll increment x by 1. You don't have to say x equals x plus 1. Just x plus equals 1. I'll let you go through this in the other texts. Okay, we'll take a quick break here. So in the news, everybody saw this. So yesterday, Microsoft surprised a lot of people with this announcement. Everybody knew Windows 10 was coming, but they didn't know they were going to do this thing called the HoloLens. So what is this thing? Well, it's a way to look cool and impress people. Obviously. You thought Google Glass was bad. Right, but what's amazing about this is it actually seems like incredible technology. It's still in the early stages, so they haven't finished developing it, and it's not product ready yet. But from an architecture perspective, what's interesting here? Well, actually, it turns out that inside this headset, they have a powerful CPU, but also a powerful graphics processing unit to work on graphics, but also something they call a HPU, a holographic processing unit. So this thing has a HPU in it, which is a new term I hadn't heard before. And actually, part of the story is this is from the same team that did the Kinect on an Xbox. And actually, you gesture in this virtual reality, it projects out to you. You gesture with your hands. And what that thing is doing partly is doing the depth recognition and gesture recognition on your hand. Now, one example they gave in their video is this one of playing Minecraft out in virtual reality. So, just in your living room, you can have all this stuff. As a parent, I think this would be great. You just turn it off and all the toys disappear. But you don't have to clear them up. But I'm not so sure I want the kid wearing this thing, right? So anyway, this is a pretty exciting, if it actually happens, you should check out the video. The video is very impressive, though apparently it doesn't, every time all the demonstrations had some minder from Microsoft, saying what you could and couldn't do with it. And because it has so much processing going on, it actually has a power cord coming out the back because they haven't quite got it down to being battery powered yet. So I guess that's one of the things they're working on. Okay, let's take just a 1 or 2 minute break. If you guys just relax, read your email. Yep. Because it doesn't take any argument. That's the way you say no arguments. Yeah, good question. Main should return an int. You'll get an error because it's a standard function. If you say it returns something else, it will usually complain and say, no, this returns an int. Main's a standard thing, yeah. So you can't redefine something to be something different. Yeah. Okay, let's just go through the last few slides. I've had a break. So one thing I wanted to point out in this HoloLens example is one of the trends in future architecture, the very specialized processing units, right? So this has a CPU, GPU, and a HPU, 3 different kinds of processor. And that's basically because the thing we told you about, the end of Moore's law. You can't just take general processors, speed them up anymore. People are now specializing processors to given tasks. That's the only way to get more performance. You'd like them all to be the same, maybe easy to program. But no, they have 3 different kinds of processor in here. Okay, just the last few slides in the last 5 minutes. Introduce pointers to you. You'll see a lot more pointers in the next lecture. So remember we said the program is stored in the memory in the computer, and the memory is just a big array of storage cells. And every one of those storage cells has a unique address, and the address is also just a number, right? So you have address 0, 1, 2, 3, 4, all the way through memory, and you may have billions of cells of storage in a modern computer, but everyone has a unique address associated with it. Now each cell stores some data value at that location. So what do you think they use to address? How are addresses? Are they signed or unsigned integers? What would you do? Signed or unsigned? Who? Signed. Unsigned. Unsigned, right. There have been some machines with negative address, but most machines use unsigned to encode. You just need a unique value for each address. Important thing not to get confused between is the address of a location and the value that's stored there. So it's like a lot of little box into which you can put different values, but each box has a unique address, right? And it's the value that changes over time. So a pointer is simply a value representing an address. It's just where something is. And it's just a number, right? So it's a variable that contains the address of another variable. It's a level of indirection. Okay, so here's an example. Here's an array of cells. This is location 101, 102, 103, 104, 105. This cell, we'll give it a symbolic name X, right? The compiler will figure out the mapping. So let's say X lives at location 104, Y lives at this location here. I can have another variable, say P, a pointer. It's just another location in memory, but it stores a pointer to here. So that all that means is this location in memory holds the number 104, 104. So that number is interpreted as the address of a different variable in memory. That's all a pointer is, right? It just contains the address of a different cell in memory. So the way this is encoded in C, the way you declare that a variable is holding a pointer is you tell the type of the thing it's going to point to, and then you have a star. So int star x means x is a pointer to an integer, okay? The way you get the address of a variable is the ampersand, is the address of operator, right? So that says x equals now the address of y. So now you get not the value of y, but where in memory it is. What number is it stored in, right? So x holds now the location of y. It's the address of it. Now, if you want to actually read the value here, if you say z equals star x, now the star is being used in the program, not in the declaration, but in the program to dereference, what we call dereference the pointer. So the star x means take the value of variable x, which is a pointer. Star says, oh, and now go look in the location that number represents. So that number is the address of some location. Star x says, take the value from that location. So star x will take the value from the location it's pointed to and assign that to z. So here's some simple examples. I declare star p and x. So p is a pointer. X is just a plain integer variable. If I now say x equals 3, this storage cell becomes equal to 3. Now the compiler is taking care of what's the address of x. That's the compiler's job to figure that out. And what's the address of p? Now the programmer says, well, p now holds the address of x. So then it will figure out the number of the cell that x is stored in and store that value in p. And we often draw that as an arrow coming from p pointing to that guy, right? So if you want to get the value, like I mentioned, use the star operator. So I can say printf, p points to %d means print it as integer. Then I say star p. So that won't print the number that is stored in this box. It will dereference p and print the value 3. So it's printing the thing that p points to, right? That's what star p does. Okay. Now, if you want to write to something using a pointer, you just use this on the other side of the assignment. So now you can say star p equals 5, and that means write 5 into the location whose address is stored in p. You're not assigning it to p. You're assigning it to the location that p points to. That's what the star p means, okay? So now you'll overwrite here. So after this statement, x will be equal to 5, okay? Now, Java and C both pass parameters by value, which means that you take a copy of whatever you put in the arguments, and that's what's passed to the function. So changing the copy can't change the original. So if you add 1 to x, if you define a function like this, add 1, notice it doesn't return anything, just x equals x plus 1. You have allocate a variable y equals 3, you add 1 to it, y still remains equal to 3. Okay? So you didn't change it. Inside that function, you changed the copy of it that was passed in as an argument. If you want to really change something, what you need to do is pass a pointer to it. So now I can say star p equals star p plus 1. So whatever p points to, so p is just an address, remember. So you're not changing the value of p, you're changing the value of the thing p points to, right? So now if you do this, y is now equal to 4, right? If you pass in the address of y, then the function will change the thing that thing points to without changing the pointer value. Okay. I'll do the rest of this next time, but just in conclusion, all data is in memory. Pointer is an abstraction of a data address. C is efficient, but very dangerous to use. Okay? See you next time.